All right. The time is 5:28, which means by the time you hear this, it's gonna be like 20 seconds after that. Um, so today I'm gonna do this a little bit differently. I'm still on the Discord voice channel, but only to listen to questions. Um, but I'm not responding on that channel. So my voice, so you should hear my voice only through YouTube, even though I can hear your voice through Discord, if that makes sense. Because I don't think Discord voice only is an issue. It's only when it is also um, combined with screen sharing, which is kind of problematic. So I still have not diagnosed the problem. Yeah, go ahead. Oh, I thought
Well,
that was a.
howdy doody.
All right. It is time. So it is 5:30, and Eric is typing something. I'm keeping an eye on the text channel of Discord. All right. So today is going to be kind of fun and kind of confusing at the same time. Um. Oh. Okay. So what we'll do is we are actually going to get started with the processor a little bit. That's going to be what your lab is about. So the first part of today's lecture is me illustrating, the processor, how it runs in Logisim, and various aspects of it. And then later on, you'll get to do the lab. So please do not try to follow me as I am doing, the steps that you might need to do for the lab, because it would be pretty hard to follow me when I'm doing it and you're trying to follow, and then you might have questions, and then plus the lag time in between, that's going to be horrendous. So let's just let me do the demonstration, and then when I pause, that would be a good time to ask questions. So I think that might be the best way to use the time for today. All right, so we'll get to share folder first. You can see this one too, even though I'm not in student view, but the top part of course information is shared folder. Everything is being streamed to YouTube right now, so it's going to be recorded. And I think I remember to set it to public this time, so no worries about not being able to access what I just did in today's lecture. So I usually just open a new tab, because I don't want to lose the other tab. So once you get there, oh, okay, great. Um, Let me see. Open in a new window. There we go. All right, so this is the share folder. Some of you might have used it already. Everything that we need to run the assembler and also to run our program is under the processor subfolder. So getting to the processor subfolder. So there are a lot of files here. Okay, so I'm gonna go. Hopefully, I'm going a little bit slow. Um, Yes, today's lab is going to be due today. Absolutely. So, now we need a few files. So the three files that you need right away would be, yeah, I have to look closer here. alu.circ. So you can just do a single click. The next one is processor0004.circ. So you can do a control click if you want to multi-select your files. And then the last one is regbank.circ. So these are the three files that you need in order to run the processor in Logisim. And they're all circ files. So once you have multi-selected multiple files, you can right click on any one of those files and then click on download. There we go. And Google is going to zip all three files, even though they're pretty small. it will zip it anyway, and then now it's going to prompt you to download. So if you have not changed your browser to give you this screen, it will just go ahead and download it into your downloads folder. Um, I usually do not like my browser to do that sort of stuff automatically, but it's up to you to control, to specify how you want your browser to function. So I'm going to change the zip file because this one is kind of long. I'm going to change it to processor.zip just so that it's easier to remember and easier to get back to. And now I'm going to switch to a command line. Now this part, you don't usually have to do it like using the command line because most of you are using Windows, and Windows can open a zip file natively, so there's no need to use a command line thing to open it. But I'm a command line kind of person, so I'm going to use the command line to do it. Alright, so here's the temp folder. I'm going to create a subfolder, which is also not necessary for you, but I'm going to do it inside the subfolder, and here I'm going to unzip processor.zip, which include only those 3 files. Okay, so here are the 3 files. So make sure that you have processor 0004 and not processor 0003, because that obviously is the earlier version. So there are certain things later on in the semester, well, not semester, in the summer session, that will only work if you are using the updated version. So let's just use the updated version from the get-go. Now, I can start this, using a script called logisim.sh, but that's because, I made this, okay, so that I don't have to retype, java-jar, blah, 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 really long command. So I can do it, because I have a little script, and you typically don't have to do it this way. You should know how to start Logisim already. So however way you usually start Logisim, just do it that way, okay? So we'll start up Logisim. And Logisim starts up with an empty circuit as usual, which is fine. And then what we'll do is we're going to open processor 0004 from inside of Logisim. So we'll open, and this is in the temp folder. So I'm going to have to go to the parent folder, then the temp folder, then the processor subfolder. And now we can see processor 0004.circ. Click open. And here we have the processor. Okay, so I know it looks really busy. It looks really intimidating, but that's okay. Okay, because we are gonna explain. I'm gonna explain, the how it works in general, what each component is, and in general how to program it. Okay, so I know it looks a little busy, it looks a little intimidating, but that's just because this is the first time we see it. All right, so I'm just zooming out a little bit here, and this is the processor. It has 2 things that kind of stands out. One is the RAM component, which we talked about yesterday, and this is the ROM component, which is also what we talked about yesterday. There are quite a few things that we haven't really talked about, and there are a few things that we have talked about. All right, so what we want to do right now is to kind of go through a opcode table. So let me go back to the share folder first. Okay, so here's the share folder. So inside the share folder, there are documents. Okay, one is called the opcode table. This is a spreadsheet, but it really is documentation. And then the other one, obviously, is assembler manual. So when you have spare time, yeah, right. Yeah, spare time. So when you have spare time, read the assembler manual, because it will tell you a lot of things about the assembler, like how to use it, how it works, and so on and so forth. But today we're going to focus on the opcode table. So I'm going to open up the opcode table, which is really just a spreadsheet. So the spreadsheet has several columns. Column A is a binary bit pattern that describes the opcode in zeros and ones only. So this is what the processor is going to see. So when the processor sees, let me pick a specific one that is easier to explain. So I'm going to pick one where it doesn't need any operands like the no op instruction. Okay, so the no op instruction, which the name, as the name implies, does not perform any useful operation, is basically just 8 zeros. Okay, 8 bits, and each bit is a zero. So when the processor reads this byte as an opcode, as an operation code, it will understand that, oh, I'm not supposed to do anything. Now later on we'll talk about why we have such a useless opcode to do absolutely nothing. Okay, the next one is called halt. It is 00000001. And when the processor executes this instruction from RAM, so this is one thing that is really important. You might want to write it down. Okay, opcode is stored in RAM. Okay, opcode, every opcode is stored in RAM, and it is read by the processor. Okay, and when the processor interprets that opcode, then it understands what to do. Should it add things? Should it subtract things? Should it compare things, and so on? So the opcode is telling the processor what to perform, what to do. So that's column A. Column A is exactly what the processor sees in an opcode. Now, obviously, it's really difficult for a human to look at just a bunch of zeros and ones and remember what the zeros and ones mean. So that's why we have column B. Column B is called the mnemonics. M-N-E M-O-N-I-C, mnemonic. So mnemonic is basically just a short name. You can look at these as abbreviations of what an operation is trying to do. And even these can be a little bit cryptic. And that's because in the good old days, people who come up with the assembler, those are all experienced programmers already. So they want to minimize the number of keystrokes so they don't have to type a whole lot of stuff. So the mnemonic is what we would rather use. So it's not like we cannot program in opcode, but it is extremely tedious, and as a result, it's very easy to make mistakes if we are to program using opcode. It's much better if we use mnemonic to specify what we want the processor to do. Now, with only column A and column B, you'll be scratching your head and go like, I have absolutely no idea what this is supposed to be doing. Well, that's why we got column C. So column C is, it specifies what an instruction does, but in a, this is also called the register transfer language, RTL. But I'm not going to explain that. Okay, I'm not going to explain what is register transfer language. So all it does is to specify operations in a form of what register is changed in what way. Okay, and we'll get to those registers later on when we get back to the processor architecture in LogicSim. And then the last column, oh, by the way, one more thing. Column C also uses the C notation to specify an operation. And as you can see, there's dereference, there's the ternary operator, and single equal symbol is the assignment operator, which means we evaluate the right-hand side in order to update the left-hand side. So it's basically just strictly in C notation, but there's no such thing as a type. Okay, so remember there's no type here. And then column D is a very brief English explanation of the operation. All right, so there are 4 columns. We have what the processor sees, what the programmer sees, an explanation in the form of how registers are updated in the processor, and a somewhat English explanation of what is going on with that instruction. So these are the 4 columns for the opcodes that we'll be using in this class. Alright, so I'm gonna pause and see if you guys have any questions. And as I stop talking, I'll be planning on what to do next. Okay, so go ahead if you have any questions. Either use the voice channel in Discord, or you can go ahead and type in Discord. All right, so I'm not hearing any questions. So what we'll do next is I'm going to go ahead and pick a specific opcode, and I'll explain that one in relationship with the components inside the processor, but only the things that we have talked about. Okay, so we'll go ahead and just do that. So I'm going to pick this one here. Okay, this column. The opcode is 1000 and then XXYY. So obviously, right away, okay, what exactly is XXYY? What are they representing? Somewhere in here, right there. So somewhere in here, it explains what is XX. XX is specified are 2 bits. In order to specify one of the 4 registers A, B, C, and D, I'll show you where they are in the processor in just a little bit. And then YY is YY are 2 additional bits to specify also a register, which also can be one of the 4 registers A, B, C, and D. They can be the same. Okay, you can specify the same register, with XX and YY. So XX is a binary bit pattern, and as a result, using 2 bits, we can specify one of 4 possible registers, and the same argument applies to YY. All right, so I'm going to switch back to Logisim right now. In order to explain, what are the XXYY, what registers are we talking about? So to do that, I'm going to have to kind of zoom in a little bit. And one of the really kind of useful component here is this guy over here. This is called the reg bank or register bank. And inside the register bank are the 4 registers that are directly addressable in software. So there are many other registers in here, like the program counter is right here. There's the flags register, which is here. There is the instruction register, which is here. But those are not directly software accessible, so we don't really count those when we consider registers that you can specify as a programmer. So as far as the programmer is concerned, there are only 4 registers. They're all contained inside this particular thing called the register bank. So now we're going to zoom in to the register bank just to take a look at what is inside the register bank. So we see input pins, output pins, and more output pins, and more input pins over here. And then we see something that is not familiar, like this decoder here, this multiplexer over here. That's okay. I'm going to explain those later. Okay. But what is most important here in this particular picture are the 4 registers here. This is register A, register B, register C. This is register D. So remember, registers A to D are software addressable. So these are the things that the programmer can specify and go like, I want to store this particular value in register C or register B, or I want to add the value of register B to register A. So the programmer has complete control over which register to use when it is one of these 4. All right, so because there are 4 registers, we need 2 bits to specify one of the 4 registers. All right, so let's zoom back out into the main circuit. And the next component I want to kind of point out is this guy over here. This is called the ALU, or the Arithmetic and Logic Unit. This is where all the computation actually happens. So let's go ahead and zoom in a little bit and see what it looks like in the inside. So once again, we see certain things that are familiar, that we are familiar with, like all the input pins, bunch of splitters, tunnels, and here we have our adder. Okay, so eventually what we want to do is to route the content of registers into the adder, and then route the output of the adder back to one of the registers. Now, how we do all that routing, I'll explain that later, because you will need to understand what is a multiplexer, what is a demultiplexer, and what is a decoder in order to understand that part. But let's just say that that's all we want to do. Okay, what we want to do is to take the value of register A and add it to the value of register B, and then store the sum back into register B. So let's just say that is what we want to do. So I'm going to type it up, because if I don't, I'm going to forget what I just said. In fact, I'm already starting to forget what I said, and so that's why I have to hurry up and do it this way. Okay, so what we want to do in English is we want to add the value of register A to the value of register B. The sum is stored in register B. So if I want to use a C notation for this, the simplest way to, or the most concise way to specify this operation is B plus equal A. Okay, I'm not sure how many of you learned this particular operator. It's called a, if I remember correctly, it is called a compound assignment operator. So what it really does is just this. Okay, it's really just doing exactly that, except it is shorter. Okay, so if you have not encountered, if you haven't encountered the first form, that's okay. Don't worry. You just need to remind yourself that it is the same as this form over here. We are computing the sum of B and A and then store the sum back into register B in this case. All right. So given this is what we want to do, how do we tell the processor to do it? So let's not worry about, how do we do all the routing, what is a multiplexer, what is a demultiplexer. Let's not worry about those because they are done already. Okay. So what we want to do is to figure out how do we specify the opcode to get this done. So for that, we got to go back to the opcode table. So here's the opcode table, and we want to find an instruction, a row in this particular table that is describing what we want to do. Well, it certainly seems to me that this is what we want to do because, well, first of all, the mnemonic is add, so that's a pretty big giveaway that this is what we want to do. And the second one is the English description is exactly add. And guess what? There's a third one. The third one is the C notation also looks like what we want to do. So let me scroll this one all the way to the top so I can display the text editor right next to it. So now we go like, but Tack, we have a problem here because in the opcode table it refers to X and Y, but in the mousepad, in the basically it's a notepad, in the text editor we have A and B. What is going on here? So what is going on is XX is a placeholder. YY is also a placeholder. So XX is, or X, I should say X here is a placeholder. Y is a placeholder. X can be one of the four registers A, B, C, or D. Y can be one of the four registers A, B, C, or D. So what we're trying to do here is to say, oh, okay. So that means the placeholder X is really B, and then the Y placeholder is really A in this specific case. Okay, so in this very specific case, that's how we want to see X and Y. Alright, so now that we have figured out what is X and what is Y in this very specific case, the next thing is, what about this XXYY thing here? Okay, when we specify the bit pattern. So when we look at the top of this spreadsheet, it says right here, XX specifies one of the four registers. If X is A, then XX is going to be 0, 0. When X is B, then XX is going to be 0, 1, and so on. In other words, XX is really just the bit pattern corresponding to the register X that we have specified. So getting back to the text editor, oops, there we go. So getting back to here, because X is register B, so according to this row over here, we want XX to be 0, 1, and down here, YY is going to be the bit pattern 0, 0. I'm going to pause a little bit, because I know there's quite a bit to digest here. Okay, and this is not going to be the only time I explain this. There'll be additional times, so I'm just giving you a taste of what is involved when we want to specify what operation we want the processor to perform. But I will go ahead and pause and let you guys ask questions. All right, I am not seeing any questions. All right, well, so if there are no questions, then we're going to go back to the bit pattern that we were looking at before, which is the add instruction. So it is right here. Okay. So the actual opcode that we want to use starts with 1000 as the most significant 4 bits of the opcode. And then the XXYY is the way we specify here. So the opcode, okay, so opcode is 1000, and then the XX is 01, and the YY is 00. So we got a question in the text channel. Can the A and B numbers be changed? I'm not really sure what that means. A is always corresponding to 00, B is always corresponding to 01. Those are the specifier of which register we want to use. Now the value of the register itself, that is runtime dependent. Okay, so the register value can change over time in runtime. But the fact that we're using the bit pattern 00 to specify register A and bit pattern 01 to specify register B, that cannot change over time. So the association between what we know as registers A, B, C, and D and the bit pattern from 00 to 11, that lookup or that association is constant. It is already made. It's basically an assumption that the assembler makes when we assemble the program. All right, cool. All right, so now we know this is the opcode. So the opcode is what the processor sees in order to execute the code. So we're going to put this into the RAM. Remember, opcode goes to RAM. Okay, and this is the von Neumann architecture. This is what the von Neumann architecture is all about. We are storing instructions in memory. Okay, and opcode is the instruction that we are storing in memory. All right, so now we go and we look at this and go like, this is in base 2. We cannot enter memory content in base 2. We have to convert it into hexadecimal to enter that in into the RAM. So this is 8-4 in hexadecimal. So I can use 16 here to emphasize that this is in base 16, or in conventional C notation, I can also use 0x as a prefix to emphasize that 8-4 is in hexadecimal or base 16. All right, cool. So we are going to go back to Logisim over here, and we're going to hard code that instruction over here at location 00. So this processor always starts executing from location 00. So if you want to test anything, you probably want to put it into location 00 as the first thing that the processor is going to execute. So now I'm going to override it with 8-4. Oh, okay, I just did something stupid here. Yeah, I think I have to change to the poking tool to actually change the content. There we go. So 8-4, and then the next one is what we call the halt instruction. The halt instruction is simply telling the processor, we are done. Okay, don't do anything further. Don't go to the next location to try to execute something. We are done. Stop doing stuff. Okay, so that's what the 01 is. It's kind of like end of line. Okay, it's in this case it's end of file or end of program, if you will. Once the processor gets to the instruction of 01, it's not going to go any further. All right. So now we want to test the execution of this program, right? Because I can talk about this all day long, and in the end, does it actually get the job done? So what we want to do is to make sure that we are using some meaningful values, because adding this 00 to this 00 and store the result, which is also 00, into register B, is not very exciting, okay? Because we cannot see the change. So we're going to have to change this a little bit. Okay, so we're going to change it up a little bit and say register A starts with a value of, let's say, 1-4 in hexadecimal. And then B is going to start with something like, let's try something in that's higher than 9, so that we can get used to base 16 math here a little bit. So let's make this one 9C. Okay, So what is going to happen is, if everything is according to what I say, what's going to happen is the value of register A, which is hard coded, okay, which is injected, okay, before the program runs by me as 1 4, and it's going to be added to the value of register B, which is 9C, okay. And let's go ahead and find out what that sum is supposed to be. Okay, so I'm gonna put this like this so that we can actually see what is going on here. So we want to add 1 4 to 9C, and we are doing this kind of the conventional way. We have a Q row, and then we have the carry row, and then we have the sum row down here. All right, first thing first, what is the single digit result of adding 4 and C in base 16? You're going to go like, what? What are we talking about here? What is C? Well, C in hexadecimal is representing what we know as 12. So 4 plus 12 is 16. Now 16 is just a quantity, okay? I'm not referring to 1 6 as a number. I'm simply referring to 16 as a quantity. So 16 as a quantity has the least significant digit being 0 in hexadecimal, but it does have a carry of 1. So we'll put a carry of 1 over here, because 1 0 in base 16 is representing exactly 16 itself. Okay, so 1 0 is the result, a carry of 1, and a single digit result of 0. In this case, we are going to assume K0 is just a 0. So 0 plus 0 is a 0. So we got a 0 here. Now we look at 1 and 9. 1 plus 9, you will go like, oh, that's easy. I know the answer is 10. Yes, the answer is indeed 10, but you should not be writing it as 1 0. Because if you write 1 0 in hexadecimal or base 16, it is really representing the quantity of 16. So the quantity of 10 is represented by a single digit of A in base 16. So A plus 1 is, because A is representing 10, so 10 plus 1 is 11, but we are not going to write 1 1, so because once again, using 1 1 to represent the quantity of 11 is only going to work if you're using base 10. In base 16, we're going to use the digit B to represent the result. So 1 4 plus 9C is B0 in hexadecimal. So that's what we are expecting to see here. Now we are ready to run the program. Now when we are running the program, there are several ways to do it. Okay, the best way to do it, if you're not trying to find out exactly how something happens, which is what we are trying to do now, because all I want to do is to go through the exercise of running some simple program in the processor, and it's the process that is more important right now, and not so much how it gets done in the processor. So if that is the case, you might want to increase your tick frequency to the maximum, which is 4.1 kilohertz, and then you just go ticks enabled. So that's going to start the program. It will have the program running at full speed. So now it's all done, and when it's all done, you can basically you can stop. You can disable ticks enabled, so you can so it doesn't automatically tick anymore. You can see register B is indeed B0 here, so the program does work the way it is supposed to, but you can see how tedious the process is. So if you are to write a longer program in opcode, this is going to be troublesome. Okay, and that's why we don't want to do it that way. We want to use an assembler instead to do something like this. So now I'm going to introduce the assembler. So in the same folder, there's a file called, oops, I just clicked on something. Let me go back to where we were. All right, so there's a file called assembler, which is this one here. It is also a spreadsheet, and if you ask around, not a whole lot of people would use a spreadsheet to implement an assembler. I started down that road like really early on, and I just did not want to do it in any different way. Okay, and there are many reasons why I want to do it in a spreadsheet. So I can go ahead and use double click to get into the assembler, if you do the same thing, it's going to be view only, okay? Because this file belongs to me, and this folder is shared read only to you. So you're not going to be able to change anything. You can click around and view things, but you cannot change a single thing. So what you need to do when you're doing your homework is go into open it. You don't even have to open it, okay? So you can go back to the folder and then just right click on it, and then what you need to do is to say, okay, let me find, make a copy. There we go. So you need to make a copy of the file that I just pointed out here. Now, if you have double clicked it and go and already have opened it, it's okay. You can go to File, and then under File there is also, I'm trying to find, make a copy right there. So in any case, you need to use make a copy. Okay. If you try to download a file as an Excel spreadsheet and try to open it in Microsoft Office, it's not going to work. Okay, so I'm going to say this once and for all. Okay, do not attempt to download the assembler as a spreadsheet and try to open it using Microsoft Office or LibreOffice or any local tool. It will only work as a Google spreadsheet. It won't work in any other way. All right, so I hope that's clear enough. And I will not be surprised if I have to repeat this like 3 more times in this session. I'll be lucky if I have to repeat it only 3 more times. So anyway, source is a tab, and what you do in the source tab is you specify the source code, okay? And you can edit the program in any way, like using just a Notepad if you have Notepad. I mean, of course you have Notepad, right? So I'm going to do the same thing. So I'm going to say add BA, which is the mnemonic corresponding to the opcode that we have just played with, and then the halt instruction, which is also the mnemonic of the second instruction that will tell the processor to go no further, because this is the entire program. So you can write your code like this, okay? Copy it. So Control C, go to the spreadsheet. Make sure you are not double clicking it, okay? If you see the blinky cursor like this, that's not going to work. You have to make sure that the cell is selected, but you're not seeing the blinky cursor. Okay, so select the cell, but do not double click it so that you can see the blinky cursor. Then you can use Control V to paste the program in. So once you paste the program in, it will assemble, quote unquote, assemble the program, which basically means it's going to convert the mnemonic into the opcode, into the zeros and ones. So it saves you a whole lot of trouble, because otherwise you have to do it for every single instruction, which is very, very tedious. There are some additional tabs here that can be very useful. The next one is the Assemble tab. So the Assemble tab, mine is abbreviated. Some of the columns are hidden. If you want to show the columns, it's actually pretty easy. You select the first two, and then I believe you just right click it, and then you say unhide columns. Then you can see all of the other columns. They're not particularly helpful, okay, when you're doing your homework. So that's why I personally would keep those remaining hidden, but you can certainly unhide those columns after you have made a copy for yourself, okay? But these 3 columns are really useful. Column V is the address of the opcode, and then column W is the content. No, I take it back. Column V is the address in base 10. Column W is the address in hexadecimal, and then column X is the first byte corresponding to the instruction of that line, and then column Y is the second byte, if there is a second byte corresponding to the instruction of that line. So I'll say that one more time. Column V is the address of the instruction in base 10. Column W is the address of the same instruction but in base 16. Column X is the first byte corresponding to the instruction of that line. And column Y is if there is a second byte corresponding to that instruction, then column Y will tell you what that second byte is. So in this case, the add instruction doesn't have a second byte, so that's why you see Y being blank. But some instructions has a second byte, then you will see both column X and column Y being non-empty. So that's the Example tab. And then we go to yet another really useful tab. Oh, okay, I forgot that I relocated that. It's the RAM file tab. So the RAM file tab is especially useful. I'm looking at the time to make sure that I'm making good time here. So it doesn't mean much to you. Okay, the RAM file tab doesn't mean much to a human being, but what you can do is to do this. Okay, so you go to File, you go to Download, and you have to select one of these two. Okay, either a CSV, a comma separated value file, or a tab separated value file. I would use a CSV, so I always use CSV when I download. So click on that one, and what it's going to do is it will prompt. Okay, I changed my browser so that it always asks me what name do I want to use and where I want to save the file. I strongly suggest that you do the same, because if a file name has spaces in it, Logisim doesn't like it. Okay, so you might want to change the behavior of your browser so that when you have a file to save, it will ask you where you want to save the file and what name do you want to use to save the file. So when I click OK here, it would actually prompt me and will ask me, okay, so where do you want to save the file? I'm going to save the file in temp processor. Actually, I can go step by step here. So let me go to temp first, and then processor is the subfolder. And if I press the enter key, it shows me what is in the processor subfolder that is ending with CSV. Nothing yet. So I'm going to just say add.csv. Now the file name is not really important. If you want to say blah.csv, perfectly okay. Even the extension is not like super duper important, because from Logisim's perspective, whatever name, whatever extension you want to use is actually okay. But I personally like to stick with CSV because that describes the content of the file. So just click save, and now the file is saved locally. So at this point, I go back to Logisim and go back to main. And the first thing I want to do, because I already got my program, quote unquote, hacked in to RAM at this point, so I'm going to go to simulate and I say reset simulation. So when I reset simulation, the RAM content is going to be cleared out like this. Okay, so this way I can illustrate to you how do you download the file from the assembler and then put it into the RAM of the processor so you can test run the program. So I'm going to right click here, and this time we use load image. And after you go there, you want to go to the folder. Okay, so I'm going to have to go back to the main folder. Okay, I'm already in the folder where the CSV is supposed to be. And right here, okay, there we go, add.csv, click open, and you can now see how the content of RAM is updated just like before, because now it has read the CSV file and then used the CSV file to specify the content of RAM. So this is okay. So you might say, but Tech, this is a lot of work for something that I could have done by hand earlier. You would have been correct, okay, because we only got 2 opcodes in this case. But imagine you're trying to implement something like the Tower of Hanoi recursively, or you're trying to implement Fibonacci, recursively. That's not going to be just a few opcodes. That's going to be a lot of opcodes. Enough opcodes that you don't want to do it by hand. Okay, so when you don't want to do it by hand, then you want to do it using the assembler, and this is the process to use the assembler to assemble your program that is written in mnemonic. Alright, so I'm going to pause because I know you guys might have some questions at this point. So I'm just looking at the clock, and I want to time myself, give you guys about 40 seconds, 20 seconds because of the lag time, and then 20 more seconds for you to ask questions. Or I can just also type in the text channel. Yep, there will be. So the practice is your lab is doing this. Okay, there are instructions built into the lab itself, so it is quote unquote self-directed. In the lab. And then Paul says on the source tab, I'm seeing a bunch of stuff already. Can I replicate your example by clearing column A of that tab first? Yes. Okay, so that's a very good question. Let me go back to the assembler and tell you what is important about that statement. All right, so if I go back to the source tab, you can see the program is mostly in column A. So you can actually select the entire column A like this. Okay, just click on the label A of the entire column and then press the delete key. That works. Okay, but you don't want to do anything to column B. Column B should be protected, but at any rate, don't try to change column B. Okay, because of the entire spreadsheet, okay, of this entire spreadsheet with all the different sheets, only column A of the source tab can be changed by you. Because if you change anything else, the assembler may not work anymore. So in that case, just make a new copy. Okay, it's not a big deal. Make a new copy. But if you suspect that you might have changed something else in the spreadsheet, just download it or make a copy again. Because if you break the spreadsheet, it's not going to crank out the right opcode. So Paul made a very good point of how to reset if you need to reset the source tab of the assembler. All right. I'm not seeing any additional questions in the text channel. All right. So that means I can use the remaining time in this lecture, which is about 35 minutes or so, to explain what the processor has inside what is inside the processor, other than the few components that we are already familiar with. Well, hopefully familiar with, because they have been introduced already. All right, so here's the processor, and there are a few things that we kind of know already. So we should know registers. Okay, so PC is a register. Microcode pointer. I know it looks like Ucode pointer, but that's because I cannot type mu. Uh, the letter, the Greek letter that looks like a cross between a P and a U. Okay, so I cannot use mu, which is micro. So I'm using U, to approximate micro. So this is microcode pointer. We have a few other registers like the flags register. We have the instruction register, and so on. From yesterday's lecture, we also know what is RAM. We also know what is ROM. Okay, so those are the things that we are familiar with. Oh, there are a few more that we should be familiar with at this point. Here's an adder. Here's another adder. This is an OR gate. This is an AND gate with one of the input negated. Let's see what else are should be familiar. This is a NOT gate right here, and another AND gate here, another AND gate here. Bunch of this is the clock pin. We talked about that yesterday or day before. Here's a button. Okay, and we have tons of tunnels here, because without the tunnels, this is going to look super busy, which is not going to be useful. What about the other components? What about this thing here? It is called a multiplexer. What about this thing here? It is called a demultiplexer. So what are we going to do with these things? Tech, you never talked about this. So what we're going to do is go to library reference. This is also why I really like Logisim, because it has a pretty good documentation to explain the components. So if we go to plexers, we can now go to multiplexer, and also the multiplexer down here. All right. So what are these things? They are basically switches. Okay, so I'm going to create a test circuit just so that we can get a pretty good idea of what those things are. So we'll make a new circuit, okay, because I don't want to mess up my processor circuit that is already in place. And then we go to plexers. And let's start with a demultiplexer. Okay, I personally think the demultiplexer is actually easier to understand compared to a multiplexer. And we'll go ahead. So we just want to look at the properties at this point. So we have select bits and then we have data bits. Okay. So now the question is, what is a select bit and what is a data bit? The select bit controls how many. Remember, this is a switch. Okay. So the way it is right now is we have one input, which is here, and it has two outputs. So one of the pins here is controlling how should I connect the input pin. Should I connect the input pin to this output pin 0, or should I connect the input pin to the output pin 1? So one of these bits here, the one under the little gray dot, let me zoom in a little bit so you can see the gray dot. So the one pin under the gray dot is the select pin. It allows us to say, how we want to connect the input pin. Should I connect to output 0 or output 1? So if I change the select pin, okay, if I change the select pin to 2, then we can now switch among 4 outputs. So there's input, the input pin, but there are 4 output pins now: output 0, output 1, output 2, and output 3. That is made possible because the select pin is now 2-bit wide. With 2 bits, I can have 0, 0 for this guy, 0, 1 for this guy, 1, 0 for this guy, and then 1, 1 for this guy. So you can also increase it even further. You can say, oh, I want 3 select pin. Now we have 8 possible outputs. In other words, the select bits is allowing you to specify what is the fan out of this switch. Okay, from one single output, what is the number of output that I can connect this input to? Now, it is probably important to point out at this point that you can only connect the input to one of the outputs, okay? And then the rest of the outputs they are not driven if it is not the one being selected. So that's how we utilize the select pin. And this is called the enable pin. The enable pin is basically doing the same thing as the enable pin of the buffered the control buffer that we talked about yesterday. In other words, if this enable pin is a 0, then the demultiplexer will do absolutely nothing. In other words, the input will not be connected to any one of the output if it is not enabled. If it is enabled, then the input is going to connect to only one of the outputs, depending on how the select pin is selecting one of the 4 outputs. Alright, so I'm going to change the data bits, which is the width of each of the input and the output pins. I'm going to change this one to a very odd, 3-bit, okay? Just so that we can see how the select bit has absolutely nothing to do with the data bits. So we'll specify the input pin, and because we made the data bit, of the demultiplexer 3-bit wide, so these need to be 3-bit wide now. And then we have 4 output pins. Each one is going to be 3-bit wide, like so. And I'm going to use the duplicate function so I don't have to. There we go. And one more. There we go. Alright, so we'll just hook up these things 1 to 1. Pretty easy here. So now you're seeing XXX because they are not driven, okay? Because nothing is driven at this point. And we'll also use an input pin just so that we can experiment with the enable. Now the enable pin is optional. You can actually make the demultiplexer always enabled by not having an enable pin. So the enable pin is actually optional. The select pin, on the other hand, is not optional because you always have to specify how you want to connect the input pin, which output pin you want to connect which output pin you want to connect to the input pin. All right, so now we have a circuit to play with, and let's specify a a less boring bit pattern. Let's try 0, 1, 0. Okay, so we'll specify the input to be 0, 1, 0. And right now, if I turn on the enable, because the select is 0, 0, 0, 0 is going to select the output 0. So if I click 1, if I change the enable to a 1, then the input pattern of 0, 1, 0 is going to be presented to the output 0, which is these 3 bits over here. So let's take a look. And then all of the other ones are driven, but they are all zeros. So I lied earlier because I said they would not be driven, but they turn out to be driven. All right, so that's what the demultiplexer does. It is really just trying to connect. It will let you specify how you want to connect the input pin, which output pin connects to the input pin. So if I were to change the select pin to 1, 0, then it would be this output pin that will become 0, 1, 0. So let's go ahead and give that a try, like so. There we go. And if I turn off enable, then all will be XXX again, which means they're not driven, like that. Let me go back to look at the properties of the demultiplexer to emphasize that you can have enable or not enable. So you see this one here, include enable and then the question mark. If you say no, then we don't have the input pin for the enable anymore, and the demultiplexer is always enabled in that case. No, they would not be XXX because they are still being driven. I know what you mean. They really should not be driven, but in Logisim they seem to be driven to 0, 0, 0. All right. Okay. All right. So if this is a demultiplexer, what do you think a multiplexer does? Let's go take a look at a multiplexer. And let me get rid of this circuit here, okay, because we are done with the demultiplexer, which has one input and multiple output. And now we focus on the multiplexer, and we're going to change it so that we have 2 select bit again and 3 data bits. Okay, so in many ways, this is the same, quote-unquote, same configuration as the demultiplexer. Do you see how this is really just the opposite? We have input 0, input 1, input 2, input 3, and 1 single output. So it's doing exactly the same thing as a demultiplexer, except the direction is opposite. So in this case, a multiplexer allows us to select one of the inputs to connect to the one output here. And once again, we have the select pin, which is the one that is doing the quote-unquote steering, which input connects to the output. And then we have the enable here. If the enable pin is a 0, then the output is not driven. If the enable pin is a 1, then the output is connected to one of the 4 inputs, depending on what the select pin is specifying. Yep, so Eric is correct. Yep. Excellent. Alright, so now we have explained what is a demultiplexer and what is a multiplexer. They are basically they're almost exactly like railroad switches, except in this case, they are directional. I'm not sure whether railroad switches are directional or not, but these are directional because they are electronics. Alright, so let's go take a look at another component. So I'm going to get rid of this. The next component is called a decoder. So here's a decoder, and it also has its own select bits. So we're going to make a select bit of 2. And look at this and go like, heck, doesn't this look almost exactly like a demultiplexer? Well, as it turns out, it really is a demultiplexer, okay? Then you go like, but it's not exactly like a demultiplexer. Like there's no input into the decoder. Well, that's because the input is a constant of 1. In other words, you can look at the decoder. Let me just make it really clear what I mean by that. So we'll put a demultiplexer on the other side, similarly configured with 2 select bits. So you can see how a decoder with 2 select bit and a demultiplexer with 2 select bit look almost exactly the same. The only difference is there's no input pin with a decoder, and there's one bit input pin for the demultiplexer. So you go like, well, can we turn a demultiplexer into a decoder? The answer is, oh yeah, pretty easy. All you have to do is to specify a 1 and connect that constant of 1 to the input. So now this circuit here, which is a demultiplexer with a constant 1 feeding into the input, is doing exactly the same thing as what a decoder would do. So that is pretty easy, right? Because a decoder is basically a demultiplexer with a 1-bit port, and you basically just specify which one of the output is going to see the 1 and the rest would be seeing zeros. All right, so let me just pause here and see if you guys have any questions. I'm just looking at the time so I can time myself, give you guys sufficient time, hopefully sufficient time to ask questions, or at least type somewhere to let me know that you need more time to compose your questions. All right, we got 2 people typing already. Nice. All right, so here's a question. Can we also just leave it open? Doesn't that imply 1? No, you cannot leave input pins unconnected, because an unconnected input pin is basically seeing interference. So it's just undetermined. It's going to be interpreted as a 0 or 1. We just don't know which one it is. So you never leave an input pin unconnected. Second question. Isn't the bit width variable on both decoder and demux? Actually, a decoder does not have a data width. See, this one only has a select bit width, but it doesn't have a data bit width. A demultiplexer, on the other hand, has a data bit width, which is by default a 1. So that's also the other difference, because a decoder basically only has a width of 1. As far as all the outputs are concerned, they're all just 1 bit wide. In other words, each one of these ports is only specifying a 0 or 1. That's what a decoder is. All right. So I just want to make this more clear. This is the base. This is same as a decoder. There we go. Yeah, absolutely. Absolutely. All right. So other than a few things, a few of the calculating thingies inside the ALU, which we don't really need to get to right now, we really have explained all of the components of the processor. So let me switch back to the processor itself, which is this picture here. And I'm going to say, well, guess what? This processor is open sourced, because you get to see how it is internally connected between all the components. And from now all the way to the end of this summer session, all we're going to do is to look at this and specify the instructions, so that we can now start to eventually we'll be able to translate C code into opcode that goes into the RAM here, in order to run programs that we can normally write in C, C++. When I say C, it means C++. It means a subset of C++. So don't be alarmed if I just say, oh, we're going to write this C program. Well, that means we're going to write this C++ program, okay? But I'm not going to get into object-oriented programming concepts. So all of those things that you learned about classes, methods, virtual methods, and so on, that's not going to be. We are not going to address those things, okay? But we will use members, okay? We'll use properties of a critical class. Basically, that's a structure. A structure is a class where all the members are public. And we are limiting only to data members. We are not going to have function members. But we will get into some interesting programs. As I said a little bit earlier, we're going to get into, let me go back to the Notepad here so we can actually see. So we will get to Fibonacci. So Fibonacci. I'm not sure whether it has one N. I think it only has one N and 2 C's. So we're going to get into Fibonacci sequence, and we're going to do it recursively, which is not efficient, not the best way to do it, but it's fun, okay, because it has recursion. And we're gonna do Tower of Hanoi. So you can look up these things, right? You can look it up and you can easily locate the C code to do it. So in this class, the focus is not the C code. The focus is how do you translate that C code into assembly code. So we're going to do both of these for sure. We can do something that is pretty easy to do in C without using recursion, but we're going to do it in recursion, okay, recursively. So we can have string compare, we can have string length, those are the easy ones. String copy, can also be one of the topics. So I'm just illustrating things that we can do using this toy processor, so that once we have the C code for these things, we can translate that C code into assembly code so that eventually we can run those inside the processor. So that's what we're going to do for the rest of this entire summer session, is to gradually get to the point where we can write code in assembly code, using mostly mnemonics, so that we can implement C code that are hopefully a little bit fun and a little bit interesting. And the example, over here are the things that we should be able to do in this class after you get out of this class. So I'm going to pause. Let me see if I have any questions down there. How does the decoder work? Okay, so that's the last question from Folin. And I mean, the explanation is really just this. I mean, the decoder is the same thing as a demultiplexer with an input of 1. That's all. In other words, once it is enabled, it guarantees that only one of the output is a 1. The rest would all be zeros. Which one is going to get an output of 1 is dependent on the input pin of select. And then the enable is optional. So if you have an enable pin, that means you can control whether all outputs are zeros, or at least or up to or 1 and only one output is a 1. If you do not have an enable pin, it implies it is always enabled, which means one of the output is 1 always. And that's dependent on how you the bit pattern at the select pin. So I hopefully that answers Fulin's question. There are no questions. All right. Well, if there are no questions, I'm just going to wait another 20 seconds because I forgot to wait. Selected output is 1. That is correct. With a decoder based on the select bit, that output is going to be a 1 and everything else is going to be 0. And that's why that's why this circuit here is exactly the same as this circuit here. This one just looks cleaner, that's all. And I believe there's only one place that I use a decoder. It's inside the register bank. Everywhere else I use a demultiplexer. All right, so I'm not seeing any additional questions. All right, so what I'm going to do is for the next, let's see, it's 37 right now. The class ends at 50. So we got about 12 minutes or so. So what I'm going to do is to show you exactly how an instruction executes. If you don't quite get it, it's probably okay, because I'm going to explain that at least a few more times. Okay. All right, so let's zoom in and go back to the memory content, which is 84 for the first byte, 01 for the second byte. And remember, these are the opcodes. Okay, these are the opcodes that a programmer can directly specify and go like, I want the processor, hey, I want you to add the value of register A to the value of register B and store the result in register B. That's what 84 is representing. So would you rather use 84 in hexadecimal, Or would you rather use the binary representation of 1, 0, 0, 0, 0, 1, 0, 0? Or would you rather use the mnemonic, which is add b comma a? Well, I mean, the mnemonic is probably easier, in the long run. Okay, so that's why we have the mnemonic and the assembler to help us so that we don't have to deal with this tedious process. But we should be able to perform that for individual instructions. Okay, so that's not really the main point. So the main point is, but how does it work, right? Just because this is how we specify the bit pattern doesn't explain how it works. So at this point, I'm going to explain how that works, and it's going to take about maybe 10 minutes or so, maybe less. So where everything starts with the ROM. Okay, so the ROM, this particular ROM here, is really the key to the operation of the processor. So what we want to do is to, okay, Joseph has a question. Are opcodes and processor instruction set effectively the same? So the instruction set, let me see. I would say yes. Opcode is from looking at the instruction set from the perspective of the processor. So they're all basically zeros and ones. Mnemonics, on the other hand, is looking at the instruction set from the perspective of the programmer. So we are looking at kind of strange names, abbreviated names, but those are the mnemonics. Because instruction set can be a confusing term because depending on from whose perspective. Does that answer the question, Joseph? Well, hopefully it does. All right, so getting back to the ROM component here. So the ROM component is really important because, now, first of all, this ROM is always enabled because it's always selected. The output, which is the bit pattern specified by the highlighted location here. So remember, 000 is the location, and then the content at that location is 1080007 in this case. And if you look at the specification of the ROM, it's really odd because we have a 12-bit address width, and then we have a very odd 26 data width. Okay, so the data bit width is 26 bits because we need 26 bits in order to control all of the components inside the processor. All right, so now we look at the output of the ROM, which is the D port, and we can see this D port has a really long bit pattern. That's really just 1080007 in hexadecimal. But it goes through a splitter. It actually goes through 2 stages of splitters. This is the first stage of a splitter, but we can see this one wire has 21 bits in it, and then it's further split from here into these additional components. And those components go to the multiplexers, they go to the registers, and so on, in order to specify what needs to be done at that instant of time. Okay, so the content of ROM, controlling the output, of this splitter and this splitter here, that really is going to specify how the different components in the processor are going to work together to get something done. So now let's go ahead and analyze, what this particular cycle is going to do. So the next question is, but how do we do that? How do we know what the processor is going to do? Well, we look for things that are enabled. Okay, in other words, if something is not enabled, we probably don't have to worry too much about it. Okay, so we always start with things that are enabled. There are only very few things that can be enabled, and I strongly suggest that you come up with a list of things that can be enabled so that you have a systematic way of going down that list in order to analyze how an instruction is implemented. So I'm going to go through this process once for you guys so that you can kind of go back to this point of the video and kind of make your own list if you want to do that. Okay, first of all, there's the register bank. So the register bank has a few enable things. So there's this RIEN, register input enable. Okay, there's the register output 0 enable. There is, I think there's one more enable somewhere, but I think that's it. Okay. And then the ALU has its own enable. Okay, this one enables the ALU itself. And then down here, the PC or the program counter has its enable. This is the enable of the program counter. And then over here, we have the enable of the instruction register. And then over here, we have the enable of the flags register. And then over here, we have the select, which is kind of the same thing as an enable of RAM itself. And then down here, we have the enable of the microcode pointer, and it is always enabled. So the microcode pointer is always enabled. It's always going to change in the next transition. So you might want to make a list of the things that I just listed a little bit earlier. If you did not, you can just kind of jot down the time right now. So you can go back to the video and then just make your list a little bit later. Okay, it's no big deal. No big deal if you need to do it later. Okay, so I'm going to analyze for this particular configuration what is enabled. All right, so let's check it out. RAM is enabled. Okay, you can see how RAM is enabled. So whenever RAM is enabled, you need to ask the question, what are we doing with RAM? Are we reading the content of one location of RAM, or are we going to update a location in RAM? So for that, you have to look at the LD. So when LD is a 1, it means we are going to read from RAM. We are going to read the we are going to read the content of a location. So now you have two questions. Okay, you should have two additional questions. One is where are we reading, and the second one is who is going to be updated based on the output of RAM. So now you have to answer those two questions. The first one of those two questions, you have to look at the A port. So you will find that the A port goes to a multiplexer. In other words, there are two possible inputs that can connect to the A port. Now you have to look at the select of this multiplexer. It is light green, which means it is a 1. So that means input 1 connects to the output of this multiplexer. And that in return goes to the program counter. So what we know at this point is the program counter is the one that is specifying the A port of RAM. It is controlling what location we are reading from. So that answers one of the two questions. The second question is who is going to be affected or updated by the data of the location that is currently selected. So now we have to track down the D port. So the D port goes to many different places. So it does potentially go into the register bank, but in the register bank we can see RIEN is dark green. It is not enabled, so we can say, nah, probably not going to update any one of the 4 registers, A, B, C, or D. You can look at the program counter, okay, because potentially it can reach the program counter. But the program counter is not going to be updated, so it doesn't really matter who connects to the program to the D port of the program counter because it's not going to be updated. You can look at the instruction register. The instruction register does have the enable pin being a 1, so the instruction register is about to be updated on the rising edge. So now the question is it going to be updated by the data port of RAM? So now you track down the D port of the instruction register and see if it is connected to the D port of RAM, and it is indeed connected to D port of RAM. So that means we are using the program counter to use the content of one memory location to update the instruction register at this point. So if I were to use the, remember earlier, I talked about the register transfer language. If I were to use the RTL language here, that means I'm going to use IR as the instruction register. It is going to be updated by reading the location that is pointed to by the program counter. So this is how I would write it in C notation, using the dereference operator to mean that we are using the program counter as a pointer. The location pointed to by the program counter will provide the value that we're going to use to update the instruction register. So that is kind of interesting. because what we are going to do, because this particular operation has a name, it's called a fetch. Okay, this is called a fetch cycle of executing an instruction. I will probably do this several times, so if you don't feel like writing it down right now, it's okay, but I would strongly suggest that you write it down now so that you have a exposure, and then later on if I mention again, you're going to go like, yeah, I know that already. This is called the fetch cycle. All right, so let's go ahead and do the fetch cycle. I'm going to do Control T, which is going to provide a rising edge because the clock is low right now, so Control T will give us a rising edge. Ding. Come on. It's supposed to happen. Oh, is it Control T? Yeah, it's supposed to be Control T. Why is it not doing it? Control T. One more time. There we go. All right, so we can see that there's a Control T, and we can also see how the instruction register now has 8-4 in it. We're running out of time, but I want to finish the execution of at least one instruction. Okay, so this way, for those of you who want to review this over this long weekend, we don't have class on Monday, so we're going to meet on Tuesday. So for those of you who want to review this, you now have the execution of one instruction, complete instruction execution. All right, so now we're going to have a falling edge. Normally, a falling edge doesn't do a single thing because everything up to this point that we have talked about are only sensitive to rising edge. There's one exception. The exception is the instruction the microcode pointer. The microcode pointer is going to update on the falling edge, and it is the only register to update on the falling edge in this case. So because it is always enabled and it updates on the falling edge, and the clock is a 1 at this point, so before I do a Control T, I really want to find out how the microcode pointer is going to be updated. To do that, we are going to track down the input or the D port and see where it's connected to. It's connected to this multiplexer. This multiplexer has 2 input, 1 output, and the select pin is going to control which of the input pin is going to be connected to the output pin. And it is light green, which means it is a 1. So that means this is how we update the microcode pointer. So when you look at this circuit here, not counting the multiplexer, that should remind you of something that we talked about yesterday, right? Because it should remind you of the counter thing that we talked about with synchronous circuit. So that's exactly what it is, okay? Because it's just incrementing the microcode pointer by 1, so it will become 0, 0, 1. So let's do a Control T at this point, and we can see how the microcode pointer is now 0, 0, 1. And we can also see how location 0, 0, 1 of ROM is now addressed. So 0, 0, 1 has its own bit pattern. So now we have to go through all the analysis again and find out what is going to be updated. I personally like to start with RAM because if RAM is selected, that will automatically answer a whole bunch of questions. Unfortunately, in this case, RAM is not updated. It's not going to be updated. Okay, fine. Now we have to go through the usual suspects. So the program counter is going to be updated. Every time a register is going to be updated because its enable is a 1, we need to ask the question, how is it going to be updated? So now we have to track down the D port, which is coming from the multiplexer here. This multiplexer has a select of 0, which means it's going to take input 0, which is the incrementing. So it's doing exactly the same thing of what the microcode pointer was doing earlier. It is just incrementing. So when I type Control T, the program counter is going to increment. And if I go back to here, so that means the next operation is really just PC++. Okay, the program counter increments itself. And now we want to see what's going to happen next. Okay, because let's do a Control T right now, and we can see how the program counter turns into 0, 1. So we are now going to have a falling edge. The falling edge will only update one register, which is the microcode pointer. But this time we can see how the select is a dark green wire, which means we are going to select the input 0. So this is going to be the interesting one. I don't have a whole lot of time today, so I'm just going to breeze through this one. So what it does is it will take the output of the instruction register, which is this tunnel here and also this tunnel here, but it's going to it's going to left shift it by 4 bits. In other words, these 8 bits of the instruction register will provide bit 4 to bit 11, and then we have a constant of 0 to provide bit 0 to bit 3 in order to form this wire here. So the 84 in hexadecimal becomes 840 in hexadecimal before we use it to update the microcode pointer. Okay, so let me do a falling edge. There we go. So we can see how the microcode pointer is now updated to 840. This is called the decode cycle. Okay, so if you want to write it down in terms of the cycles of executing an instruction, this is called the decode cycle of instruction execution, because it goes to a location in the ROM that specifically implements this particular instruction, which is add BA. So this particular bit pattern here will control the rest of the processor so that we accomplish the addition of whatever is in register A to whatever is in register B and then store the result in register B. I will go through this really quickly just so that we finish the explanation of this entire thing. First of all, we will see that RIEN, register input enable, is light green, which means we are going to update one of the registers in the inside. And then we will also see how we are routing out 0 and out 1 to the ALU. So out 0 goes to this demultiplexer. The select of this demultiplexer is a 0, 1, which means the input is going to be connected to the output 1 here, which goes to the first input of the ALU. We do the same analysis of out 1. It goes through a smaller demultiplexer, which has the select being a 1. So that means it's going to go to this wire, which then in return is going to another multiplexer, but the other multiplexer has a dark green as the select bit, and as a result, input 0 is let's see, what am I saying here? So input 0 is going to input 0 of this multiplexer, which is coming out from here, is now connected to in2 of the ALU. So this is how we know out 0 and out 1 of the register bank are connected to in1 and in2 of the ALU. I guess I really cannot finish the explanation. So for those of you who want to explore this on your own, I will finish this on next Tuesday. But if you cannot wait, okay, and this is why I really like this way of organizing this class, is you can go ahead and just right click and find out, okay, what is going on here? Who is connected to register output 1, output 0? So you just trace your way back, find out that input 0, 1, which is this guy here, is connected to this pin, which is register B. Who is connected to reg out 1? Track down this wire, track down the select pin, and then you find that it is register A that connects to register output 1 select. So that is why you can also go to the ALU and find out what are we going to do now that we know which register connects to in1, which register connects to in2. What is this going to do? Once again, go to the select pin. The select pin is 0, 0, 0. So that will configure this demultiplexer, this demultiplexer, this multiplexer, and a whole bunch of other things. But eventually, you will find that, oh, we are just hooking up this in1 to this input of this adder. We're going to connect this in2 to this input of this adder, and then we'll connect this output of the adder to the actual result of the adder, of the ALU. And then the output of the ALU, which is here, this wire, goes all the way back, through a multiplexer back into the register bank, and the register that is going to be updated is the one that is enabled. You can see this is the only use of the decoder in this design, and we can also, well, it may not be the only one. There may be another one, but this is one of the applications. So we can see how register B is the only one that has the enable pin turned light green. So register B is going to be updated. Now we want to see how it's going to be updated. We look at the D pin. It just connects to register in. And that's how we accomplish adding the value of register B to the value of the other way around. Sorry, this is how we add the value of register A to the value of register B and then update register B. I know I was rushing. I will do this in a slower pace on Tuesday. But if you cannot wait and you're curious about this, you can track down everything now because I have just explained how every single component function in the processor. So it's all a matter of just reading the map and figuring out how to get from point A to point B. I know I'm making it sound like a whole lot easier than it really is. But with practice, it really is that easy. Alright, so I'm going to open up tonight's lab, and because I keep yakking, past 50, I'm going to give you back, that 10 minutes or so. So we are moving on to, I'm just looking through. Oh, this is the lab that we are doing right now. It's called Familiarizing with the TTP Text Toy Processor Tool Chain. So we'll take a quick look here. I believe this one has a passcode. And of course, I cannot remember what the passcode is. It does allow multiple attempts, okay? But you do have to turn it in before 8:30 p.m. tonight. Oh, the passcode is Johnny. Let me just type it in the text channel. So obviously that is coming from von Neumann. I really don't think anyone would call him Johnny, but so today is July 1st, and we'll make it due at 8:30 p.m. July 1st at 8:30 p.m. and then save and publish. There we go. Alright, so now you have your lab open. There is one question that has to do with how to interpret the Assemble tab. So for that one, you might want to remember what I said earlier in class about column X and column Y, because that's going to be really helpful to help you answer that question. Alright, so I'm going to step away for 10 minutes and then I'll be back. Just remember, the spreadsheet doesn't work if you download it onto your local computer. Just make a copy and then use that copy from your own Google Drive and everything should work. Alright, so I'll be back at 7:10 to answer questions, but right now I'm going to go get something to eat.